2 10-hours, my inspection log, 1 locking pin, half-seated. I issued the clearance anyway. 3 pushes, the engine stopped, fuel pressure fell to 0. The report was sealed before dawn. In 1942, British planning treated airborne forces as a tool for short-notice seizures and disruption. The war stage was defined by industrial strain and by the need to open a future front in Western Europe. Britain was also sustaining the Soviet Union through combined pressure on Germany. That larger alignment did not change the small problems faced by a paratrooper after landing. It made those problems more urgent. German units reacted quickly to drops. Local patrols and reserves moved to roads and junctions. A unit that could not rally and move in the first hour often lost its initiative. Existing mobility options did not fit airborne constraints. The men on foot were slow under heavy load. Bicycles were awkward in aircraft loading and easily damaged in drops. Full-size motorcycles could not be packed into the standard light equipment canister used for parachute delivery. Gliders could bring vehicles, but glider numbers were limited, and landing areas were uncertain. The procurement requirement that survived was narrow. A one-man vehicle that could be dropped by parachute inside an existing container already accepted by the system. This requirement was bound to bureaucracy. Aircraft load plans, parachute rigging schedules, and container dimensions were fixed. The container, light equipment canister, imposed a hard envelope. A compact vehicle was acceptable only if it conformed to that cylinder and survived impact. The need was stated without ornament. Reduce time from landing to the movement. Enable a small number of men to cover miles on roads and tracks to link scattered groups and deliver messages. The work was directed through SOE's Station 9, an engineering and development centre near Welwyn. Station 9 produced multiple Well devices. A folding motorcycle followed the same naming pattern and became the Welbike. The project was not a motorcycle company initiative. It was a response to an airborne form factor and to a time problem. The design had to use ordinary manufacturing methods and components that could be sourced under wartime allocation. The concept was simple in outline: a frame that folded, handlebars that rotated flat for packing and locked upright for use, a seat pillar that telescoped, footrests that folded out, and a small engine mounted low to keep packed height within limits. In practice, each simplification removed margin. Parts deleted to save height and weight reduced safety and field tolerance. A folding vehicle exposes joints, pins, and clamps to dirt and shock. The engine selection reflected production reality. A 98 cubic centimeters Villiers single-cylinder, 2-stroke unit was used. 2-stroke operation reduced complexity and parts count. Ignition by flywheel magneto removed dependence on a battery. The transmission was single-speed. Power was sent by chain drive. This avoided a gearbox with multiple ratios and the machining it would require. The cost of that choice was performance with a fully equipped rider. Early design work is associated with Station 9 leadership and staff, and including Lieutenant Colonel John Dolphin and engineers linked to the SOE development team such as Harry Lester and Ken Taylor. Prototypes were tested for packing, drop survival, and rapid deployment. Once the concept survived basic trials, the design moved into a production pathway. Excelsior Motor Company in Birmingham was contracted to manufacture the motorcycles. This required allocation of space, labour, and inspection capacity within a wartime economy already saturated by priority contracts. Container geometry drove the entire machine. The standard canister length was about 51 inches, and the packed machine had to sit within a height of roughly 15 inches and a narrow width near 12 inches. The Welbike achieved this with small wheels and a short wheelbase. Wheelbase was about 39.5 inches, overall length was about 4 feet 3 inches, so wheels were around 12.5 inches in diameter with narrow tyres. The frame used a twin-loop tubular construction that could be welded quickly. There was no suspension, there were no lights, there was only a rear brake. Each emission was a weight and height saving. Each emission created a practical risk in use. Manufacturing was simplified to match the device's expendable role. Tubing could be cut, bent and welded with standard jigs. Small brackets were minimized. Non-essential road fittings were deleted. The machine could be finished rapidly, with paint applied as part of a streamlined line process. Production remained limited rather than universal. Between 1942 and 1943, about 3,641 units were built, plus prototypes and pilot machines. Minor variations appeared during production to address reported issues, and including changes around mudguard fittings and fuel-filling arrangements. Procurement friction appeared early. The Welbike depended on small engines that were also demanded for other light transport and generator applications. Villiers production had to be scheduled against higher priority programs. Tyre allocation competed with truck and aircraft ground equipment needs. Rubber was a controlled material. Some design changes reflected that environment. Handlebar grips could be produced in brass and canvas rather than rubber when rubber supply was tight. Fasteners and pins had to use standard thread forms already in store. Any requirement for special alloys would have delayed approval and raised security handling costs. Manufacturing steps were arranged for speed rather than refinement. Tubing was cut to length and bent in fixtures. The joints were welded rather than bolted where possible to reduce parts count. The engine cradle and chainline were set by simple jigs. Controls were routed with short cables to minimize snag points in the container. Each completed frame went through basic alignment checks because a small deviation in a short wheelbase changes handling quickly. Engines were installed and run briefly for function, then drained and prepared for storage. The fuel tank pump and sealing faces were checked for pressure retention because fuel feed depended on it. Final inspection included verification that folding joints locked cleanly and that spring pins engaged fully. After inspection, the machine was folded, strapped and loaded into the canister with protective packing around exposed levers. The container itself then became part of the supply item and required its own inspection cycle. Rejected alternatives were discussed in parallel because the concept was not self-evident. Some proposals centered on motorized bicycles, which were lighter but still awkward in a canister and vulnerable to wheel damage. Other proposals assumed that gliders would solve the mobility problem, but glider lift was rationed and glider losses were expected. A small scooter format was also possible, but the wheel and steering geometry still struggled within the canister envelope. The folding motorcycle was accepted mainly because it could be reduced to a narrow package while still using a conventional engine layout. Testing was repetitive and procedural. At best, the key question was whether the canister and the motorcycle survived impact without hidden damage. Drop tests exposed the weaknesses of folding hardware. A pin that remained reliable in workshop handling could jam after a hard landing. Seat clamps that held under static load could slip after repeated shocks. The tank pump seal could leak after vibration. Each fault produced a change request. Change requests had to be weighed against production disruption and against the need to keep parts interchangeable. The outcome was incremental improvement rather than redesign. Technical layout was built around a direct propulsion chain. The two-stroke engine drove through its primary transmission to a single-speed output. Chain drive transferred torque to the rear wheel. A flywheel magneto supplied spark without external power. Then air cooling eliminated hoses and radiators. Exhaust routing was tight because the machine had to fit the folded profile without protrusions that could catch in the canister. The fuel system formed a simple chain. Tank fuel was pressurized by hand pump. Fuel was then pushed to the carburetor and into the cylinder through the intake. Combustion required correct mixture because lubrication depended on it. Any interruption in the pressure interrupted the entire chain. Mark changes illustrate how the supply system handled faults. Early machines are often described as Mark I. Later production included Mark II variants with small fitting changes. Reports mention additions such as mudguard changes and altered filler arrangements to reduce servicing delays and leakage risk. These were small alterations, but they show that the bike was treated as equipment under revision control rather than as a finished consumer product. The central engineering compromise was fuel delivery. A conventional gravity feed was difficult because the tank could not sit high. The Welbike's tank sat low, below the carburetor feed point. Fuel therefore required pressure to reach the carburetor. A hand pump was integrated into the tank assembly to maintain pressure. This made the system workable in a compact package. It also introduced failure modes. Damaged seals or joints could leak pressure and stop fuel flow. Maintaining pressure with compromised fittings could force fuel outward. The pressurized system added handling risk during storage, carriage, and immediate use. The engine demanded correct two-stroke fuel mixture. An oil was mixed with petrol rather than carried in a separate sump. This reduced engine size. It increased dependence on correct fuel preparation and supply discipline. In airborne operations, fuel availability and measurement were not guaranteed. Improper mixture could reduce power or seize the engine. A seized engine converted the bike into dead weight. Controls were minimal. There was a throttle and ignition control. There was no kickstarter. Starting was by push start. This saved space and parts but required firm ground and time. Wet grass, mud, rubble, or slope reduced the chance of a clean start. A single-speed drivetrain also reduced starting flexibility. If the engine bogged under load, the rider had to stop and repeat the start process. Braking was limited by design choice, rear brake only, no front brakes issued. And in road terms, this increased stopping distance and encouraged rear-wheel lock. On small wheels, a locked rear wheel can skid abruptly. Without suspension, bumps transferred directly to the rider and the frame. This affected steering stability and increased loss of control risk at even moderate speed. Accepted performance figures were modest and specific. Dry weight was about 32 kilograms. Fuel capacity was about 6.5 pints, roughly 3.7 litres. Expected road speed was around 30 miles per hour. Expected range on a full tank was about 90 miles in favourable conditions. These figures suited short movements between a drop zone, a rally point, and a road objective, if a road existed. Packing and delivery were system features, not accessories, and a Welbike was placed into the light equipment canister with attention to handlebar position and lock safety. The canister was parachuted separately from the soldier. That separation created an operational contradiction. The bike could only save time after it was recovered. Airborne dispersion was normal, increased by wind and flak. A man issued a Welbike might land far from it. Searching for the container could consume the time the bike was meant to save. Training therefore concentrated on procedure. Identify the container canopy, open the canister, extract the folded motorcycle without bending controls, rotate and lock the handlebars on spring-loaded pins, raise the seat pillar and secure it, fold down the footrests, pressurize the fuel tank, check throttle movement, push start and ride. Demonstrations could show quick deployment under controlled conditions. Field conditions were not controlled. Containers landed in trees, water, hedges and soft ground. Latches could jam, parts could be bent. The design's tolerance for these outcomes was limited. Failure points were common mechanical faults amplified by context. Locking pins could jam with dirt or impact deformation. Partial engagement could allow sudden handlebar movement. Seat clamps could slip if contaminated or worn. Fuel pressure loss could starve the engine. Water could disrupt ignition until dried. Debris could block carburetor passages. Small tyres could sink in soft ground. Mud could pack around the wheels and stop rotation. Each failure reduced the unit's ability to rely on the device in its intended time window. An operational issue, it went primarily to airborne formations rather than clandestine SOE teams. SOE infiltrations often depended on concealment and local transport. A small motorcycle required fuel, created noise, and was limited off-road. The Welbike was issued to British airborne forces, including 1st and 6th Airborne Divisions. It was used in the European theatre. It was present in airborne operations, including Arnhem, during Operation Market Garden in September 1944, and it is associated with airborne landings in Normandy in June 1944. Its employment was practical and narrow. Use roads and firm tracks to move a messenger or link scattered groups. Abandon the bike if it compromised the mission. Field reports indicated mixed outcomes. When a rider recovered the container quickly and found a usable road, that the Welbike could provide real-time savings. It allowed rapid movement between separated elements and reduced the need to allocate multiple runners. It could also be written off without severe loss if contact or enemy fire made riding unsafe. When conditions were degraded, the device failed to deliver value. If the container could not be found, there was no bike. If the engine would not start, there was no bike. If the route was mud or broken ground, speed collapsed. The same small wheels and lack of suspension that enabled packing became the performance limit. The device carried risk in use beyond enemy action. Rear-only braking and small tyres increased fall probability. Push starting under stress could expose a man in open ground. Pressurized fuel tank introduced leak and fire risk. In administrative language, these risks created reluctance. Operators who experienced failures were less likely to plan around the bike. A tool intended to compress time cannot succeed if users hesitate or avoid it. Institutional assessment followed resource accounting. Each Welbike consumed an engine, tyres, tubing and production time. Spares, storage and training hours were also required. Maintenance burden increased in units already carrying new radios, demolition stores and specialised airborne equipment. As glider delivery capacity improved, heavier and more capable vehicles could arrive with troops rather than under separate parachutes. Gliders could deliver jeeps and full-size motorcycles directly to units, reducing the dispersion problem. The Welbike's niche narrowed further as doctrine and lift capacity evolved. Enemy countermeasures did not need to change. A folding motorcycle did not alter German air defence or doctrine. At most, it appeared in captured equipment notes as evidence of British airborne mobility experimentation. The practical counter to a motorcycle was already in place: roadblocks, patrols, and rapid reaction drills. The Welbike therefore had no strategic effect beyond marginal movement within a small time window. By late war, the device was not expanded into larger procurement. Issue remained limited, and secondary use on airfields and urban depots was common, where hard surfaces reduced weaknesses. Its decline was administrative. The system reduced distribution as better transport options became available, and as the cost-benefit case weakened. After 1945, surplus disposal highlighted the same design omissions. That without a front brake, the motorcycle did not meet normal road requirements without modification. Some machines were sold off as surplus. The foldable concept continued in civilian form. A post-war descendant appeared under the Corgi name through Brockhouse Engineering, developed from the same general idea but altered for civilian expectations. Post-war evaluation often split between admiration for packaging and criticism of field performance. Technical review is direct. Compactness met the container standard. That same standard removed suspension and front braking. Road movement was viable only on firm surfaces. Rough ground reduced speed and control sharply. As a primary plan for dispersed landings, the device was not dependable. Within the record, the Welbike shows equipment shaped by delivery constraints rather than by rider preference. Its unfolded appearance was ordinary. Risk came from missing safety systems and from the pressurized fuel feed. Usefulness depended on recovery, starting conditions, and access to roads. This weapon was a technical decision born from wartime pressure, effective on paper, limited in the field.